So just to kind of recap on everything we've covered. So we've talked about symmetry, and we discussed the different types of crystallographic symmetry we can have. And now today we're going to be discussing crystal systems, Bravais lattices, and crystallographic point symmetry. Now you see we did talk about molecular point symmetry on the last two lectures, but we have what's called crystallographic point symmetry, and we'll be discussing that. And then if we finish that up today, the next lecture we'll be talking about space groups, site symmetry, general and special positions as well. So just to recap on the crystal systems that we've been discussing. So there are 7 crystal systems depending on their lattice parameter constraints. So we have, of course, cubic, tetragonal, orthorhombic, monoclinic, hexagonal. Now rhombohedral can be used intertwined with trigonal. So sometimes you may see it rhombohedral, sometimes you may see it trigonal, but they're the same crystal system, not trigonal, trigonal. So whenever you rhombohedral is actually a subset of trigonal. So don't be alarmed if you see rhombohedral or trigonal. They're the same, considered the same crystal system. Now the way that you know that something is trigonal versus rhombohedral is based on the centering. So for trigonal, the centering is generally primitive, a P in front of the space group. Rhombohedral is going to be R as the first letter in the space group. So that's how you can distinguish between trigonal and rhombohedral. Trigonal is going to be what we'll see in a little bit, primitive centering. It means the space group, the first letter is a P, and rhombohedral, the first letter in any of those space groups will be an R. So that's how you distinguish between trigonal and rhombohedral. And by the way, rhombohedral is the only crystal system that has R centering. So you can't get it confused with anything else. It's a very unique crystal system. So if I was to rank these from highest, what we call highest symmetry to lowest symmetry, where one being the highest symmetry means it has the most symmetry or most symmetry elements in it, and 7 being the lowest symmetry means it has the fewest symmetry elements in it. And so the highest crystal system, highest symmetry is cubic. Then it would be, similar to maybe hexagonal, trigonal, tetrahedral, orthorhombic, monoclinic, and triclinic. So cubic is the highest symmetry crystal system, meaning it has the most symmetry elements. Triclinic is the lowest symmetry, meaning it has the fewest symmetry elements. And in fact, triclinic, there's only one symmetry element in either of the triclinic space groups. Now, the other ones you should remember are things like orthorhombic, monoclinic. So these are common crystal systems. So I'm going to underline the common crystal systems that we see. And those are going to be your triclinic, monoclinic, orthorhombic. And what you should remember about these three is that orthorhombic is the highest symmetry crystal system from the 3 shown here, because about 80 to 85% of your crystal structures for organic compounds and organometallic compounds will crystallize in one of these 3 crystal systems. In fact, in my experience, I think I've only ever once got a crystal structure that was tetragonal and once maybe trigonal crystal structure. So these are very rare. Like I said, 85–90% of the time, you're going to get one of these 3 crystal systems. So what we're showing you here is in each crystal system, the type of rotational symmetry that can be present. And this is very important because based on the space group, you can determine the type of crystal system. And so it's important to know what type of rotational symmetry you can have in these crystal systems. So for triclinic, the only rotational symmetry is 360 degrees, aka the identity. So you just rotate it 360 degrees and you get the same thing. So that's the only rotational symmetry, excuse me, in triclinic. Now the lattice parameters, of course, triclinic, none of the cell lengths equal each other, and alpha, oh, that's not right. So alpha doesn't equal beta, doesn't equal gamma, doesn't equal 90 degrees. So all the angles are different. Now monoclinic, if we're starting from the lower symmetry to higher symmetry, monoclinic is the first crystal system that incorporates twofold rotation. So monoclinic can only have twofold rotation. So if you look at a space group and it has fourfold rotation, it cannot be monoclinic. And monoclinic only has one unique axis, the B axis. So that's the primary axis in a monoclinic system. So anytime you see a symmetry element for a monoclinic system, it's always about the B axis. And so you have twofold rotational symmetry in the monoclinic system. And then again, the lattice parameters, A doesn't equal B, doesn't equal C. Alpha and gamma are 90, but beta is something that's not 90 degrees. Now, when I show you our next, when I do unit cell indexing on the single crystal diffractometer, the lattice parameters are determined based on the diffraction data. So this is something that they can calculate very quickly when you have diffraction data. Now we go to orthorhombic. Orthorhombic only has twofold rotational symmetry. Now for orthorhombic, as we'll see later, it has three unique axes, A, B, and C. So A, B, and C are unique axes for orthorhombic. So that means when you see an orthorhombic space group, it's going to have three operators. So just to give you an example, monoclinic P2 upon C, that would be a monoclinic space group. Triclinic P1 bar, orthorhombic could be P2, P2, 2. So each one of those twos represents a unique axis, A, B, and C. Now tetragonal, we'll talk about their unique axis later, but generally tetragonal, the unique axis is C. And for tetragonal, you have primarily fourfold symmetry, and you could have twofold symmetry. But again, with tetragonal, the main rotational symmetry is fourfold. In addition to the fourfold, you could have twofold symmetry, but the primary one is 4. So if you see fourfold symmetry, it's a good indication it could be tetragonal. However, if you notice at the bottom, cubic does have fourfold, but there are ways that we can distinguish between the two that we'll talk about later. So tetragonal is close to orthorhombic, except that A equals B and those don't equal C. So it has a little bit more constraint in the lattice parameters. Trigonal rhombohedral, the primary rotational symmetry is 3. However, you could have, in addition to the threefold, you could have twofold rotation. And for trigonal rhombohedral, A equals B equals C, but the angles not equal to 90. So there's some angle, but they're all equal, but not equal to 90 degrees. And rhombohedral cell is what we call R-centered, and it shows you down at the bottom the lattice points for a rhombohedral unit cell. Hexagonal is very easy to identify because the primary rotational symmetry in hexagonal is always six-fold symmetry. Oh, I forgot to write a. So for this one, it could be, for tetragonal, it could be P4 upon 1. Trigonal could be P3. Rhombohedral could be something like RM, so it has a mirror plane. Hexagonal, P6. And then we get to cubic, and cubic has, and it's a little bit tricky, but typically it has fourfold in addition to threefold and twofold symmetry. So cubic has a variety of different types of rotational symmetry. So if you see a space group that contains a fourfold and a threefold, or fourfold, threefold, and twofold rotational symmetry, it's a good indication that it is cubic. And again, cubic has the greatest restraints on the lattice parameters, so all the lengths equal the same, and alpha equals beta equals gamma equals 90 degrees. And I don't use cubic that much, and as you can imagine, I don't exactly know a cubic space group, but I think one would be, for example, P432, for example. This is not a very common crystal system. So again, the main thing to notice on this slide is A, the rotational symmetry constraints for each crystal system, and B, the lattice parameter constraints for each crystal system. And again, the lattice parameters can be calculated very quickly once you have an initial set of diffracted patterns. And again, when I post the unit cell indexing video, you'll see how this is very quickly done. In like 5 minutes, you can determine the type of crystal system your crystal has. Now, the actual solving the structure takes more data, but the lattice parameters can be calculated very quickly. So we talked about the rotational symmetry. In crystallography. We also have what's called point group symmetry groups. Now, point group symmetry, what it does is it removes all the translational symmetry and just looks at the point group symmetries for different crystal systems. So again, point group symmetry removes the translational symmetry and just tells you what point groups can be present in these crystal systems. So when I mean removes translational symmetry, what this means is if one of the crystal systems has a screw axis, say it's 2/1, it would get reported as just 2. So it would be a point group 2 could represent a 2/1 screw axis, or it could represent a twofold rotation. Because remember, point groups don't have translation. It's only rotational or reflection symmetry. And so as you can see here, and this is a very important chart, and I'll post this updated chart on Blackboard, but for cubic, you have 5 different point groups. And within these point groups, you would have different space groups that could fall into these groups. So for cubic, one of them is M3M. So when you see 3 symmetry elements in a row, this represents the A, B, C axis. Because for cubic, you have all the axes listed. Now, when you see just 2 of them, what this means is that you have the primary axis and the secondary axis. And again, when we talk more about the space groups, we'll go into what's the primary axis and secondary axis for those higher symmetry space groups. But for a cubic, you could have a mirror plane, a threefold, and a mirror plane, and that would be a cubic space group. So a mirror plane, 3 mirror plane. Now this can be a variety of things. It could be a mirror plane, threefold mirror plane, or it could be maybe an A glide, a 3-1 screw axis, and a B glide. Because again, point symmetry removes the translational symmetry. So when you see a mirror plane and a rotation and a mirror plane, that could be what it says, or it could also be a glide plane and a screw axis. And so you'll notice here that cubic systems, you see, in all of them, they have threefold rotation. And the ones with a fourfold, it also includes a threefold rotation as well. Now, when we go to tetragonal, tetragonal has a 4 upon M, MMM, and other types of point group symmetry. And what you notice here is that for tetragonal, the common point symmetry group is a fourfold rotation. So every tetragonal space group will list a fourfold. It could be a rotation or it could be a screw axis in the space group. So if you see a fourfold rotation or screw axis in a space group, automatically you should know it's tetragonal, because that's the unique characteristic in all tetragonal space groups. Next we go to hexagonal. Again, from the point groups, you'll notice that the common theme in all point groups for hexagonal is they have a 6-fold rotation. And so if you have a 6-fold rotation, this could be a rotation or it could be a 6-fold screw axis, then you know automatically it's hexagonal. So these are important characteristics to remember when we're assigning space groups. So if you look at your space group and you see that the first element is a 4-fold rotation, automatically you should know it's going to be tetragonal. If it's a 6-fold rotation, automatically you should know it's going to be hexagonal. Now when we get to trigonal and rhombohedral, of course, rhombohedral, the way you know it's rhombohedral, it has an R as the first letter in the space group. But for trigonal, you'll notice here that the first symmetry element is going to be some type of 3-fold rotation. Now what I want to stress is if you look at cubic up here, you'll notice that the 3-fold is not the first symmetry element listed in the point groups. So for cubic, the 3-fold would not be listed first. But for trigonal, you notice that for every one of the different point groups, a 3-fold rotation is listed first. So you're always to know if it's the difference between trigonal and cubic is looking at, okay, when I see the space group, does it list the 3-fold first? So for example, let's say we have this space group PM3 bar, and we want to compare it to P3 sub 1, 2. And we have these two space groups, and you're asking, okay, which one is trigonal? So what you would do is you'll look at both of them and see which one has a 3-fold rotation listed first, and that would be this one. So the P31 upon 2 would be a trigonal space group. The PM -3, since 3 is not listed first, it's going to be a cubic space group. And that's how you can tell the difference between trigonal and cubic. Trigonal means that the 3-fold rotation, which whether it could be a screw axis or rotation or roto inversion, is listed first. Now the next two, we have orthorhombic and monoclinic. And you'll see that both of these have 2-fold rotation associated with it. But what you'll notice, the difference between orthorhombic and monoclinic is that orthorhombic has 3 symmetry elements for each point group, whereas monoclinic only has 2 or 1 symmetry element for each point group. So orthorhombic monoclinic can only have twofold symmetry. So if you see twofold symmetry is, in those space groups, generally it's going to be either orthorhombic or monoclinic. Now the way you determine the difference between orthorhombic and monoclinic is whether the space group has 3 symmetry elements or 1. So for example, if we're comparing P to 1 upon C or PBCA. So you have 2 space groups. You want to determine whether it's going to be monoclinic or orthorhombic. What you're looking for here is that this one has 3 symmetry elements. It has a B glide, a C glide, and an A glide. And that's characteristic of this point group here, the MMM. So since this has 3 symmetry elements, it's going to be orthorhombic system. Since the P21 upon C only has 1, or you could say in some cases 2, it's going to be monoclinic. And that's how you determine the difference between orthorhombic and monoclinic. If monoclinic, it only has 1 symmetry element, or at most 2, as in this case. Orthorhombic will always, and that's always in caps, always have 3 symmetry elements in the space group name. These can be mirror planes, glide planes, or twofold rotations, or 2-to-1 screw axes. Now triclinic, it's very easy because it has no rotational symmetry, no reflection symmetry. There's only 2 space groups in triclinic, and that is P1, which is designated space group number 1, and P1 bar, which is space group number 2. So those are the only 2 space groups that are triclinic. And again, what you're seeing here is there's no rotational symmetry, there's no reflection symmetry. You either have the identity as in P1 or you have the inversion center as in P1 bar. That's it. No other type of symmetry is present. And so again, understanding this chart here is very important in kind of assigning space groups to crystal systems, because only certain crystal systems can have certain types of point symmetry. And so hopefully when I post this, you take another look at it, kind of review over it, so it'd be easy to assign space groups to crystal systems. All right. And so just to kind of, we did talk about this early on in the first couple of lectures, but based on the symmetry of the crystal, you can simplify the volume calculation. So as we mentioned early on in the class, this was the big equation that was used to determine the volume of a unit cell. And of course, with the more restrictions in the lattice parameters, it does simplify the volume equation very, very well. So triclinic is probably one of the worst ones to calculate the volume by hand, because you see you have all these cosine squared, alpha, beta, gamma, etc. But with monoclinic, since only beta is non-90, it simplifies the equation quite a bit. And then even with orthorhombic, tetragonal becomes even simpler. Then of course cubic is the simplest because it has the most lattice most lattice restraints. This is showing you the crystal system does affect the equation for volume calculation. So here I want to show you some interesting facts about the 7 crystal systems. And again, by knowing the crystal system and the symmetry, we're able to get eventually the space group and the atomic positions. And so what we're seeing here on this top graph is the number of space groups in the crystal system, the number of structures that were published for inorganic structures and organic structures for the different crystal systems. And what you'll notice here is that for triclinic, which is called anorthic crystal system, there's only 2 space groups, space group 1 and 2. For monoclinic, it goes from space group 3 to 15. Now you're expected to know in this class the first 20 space groups because those are very important. So you should know all the space groups for monoclinic, and we'll talk about these in the near lectures coming up. But those are very important because in most cases, as we'll see in the graph below, you're going to be dealing with space groups in monoclinic, triclinic, and orthorhombic systems. So it's very important that you understand those space groups from those 3 crystal systems. Now with orthorhombic, it's 16 to 74, but as long as you know the first few orthorhombics, we're talking about up to space group 20, then that's okay. The rest of them, you'll kind of get the idea of how it works. Then tetragonal, of course, is space group numbers 75 to 142, hexagonal 143 to 194, and cubic 195 to 230. So these are actually numbers that represent different types of space groups. So in all, there's 230 space groups. Oh, actually not. There's a little bit more than 230 because there's no trigonal listed here. And so what you can see is that for inorganic structures, the main 3 crystal systems are orthorhombic, hexagonal, and cubic. They have the most inorganic structures. And some may even say tetragonal as well is a pretty good crystal system for inorganic structures. And inorganic structures, we're dealing with things like that don't contain any organic components, so like salts, etc. Now what I want to draw your attention to, and this is the important thing, especially at this university, we do a lot of organic, organometallic structures. And what you see here is that the majority of organic structures come from predominantly 2 main space groups, monoclinic, or 2 main crystal systems, monoclinic, orthorhombic, and then of course triclinic is a main one as well. So these 3 crystal systems, triclinic, monoclinic, orthorhombic, make up about 90% of all the crystal structures for organic or organometallic compounds. Now, back in 1998, there was a CSD search done showing you the number of crystal structures for organic structures, what systems they crystallize in, and as you see for triclinic, 20% of the organic structures crystallize in triclinic, 53 crystallize in monoclinic, and about 21% again crystallize in orthorhombic. And so if we were to add up, let's see, 42 plus 53. So 95% of all organic structures crystallize in these 3 systems. 95%. I mean, that's a big. I know it's back in 1998, which is 20 years ago, but still, I mean, 95% of every organic crystal structure was crystallized in one of these 3 crystal systems. And what you're seeing in the figure 2 is here we have organic structures, just another bar graph. And then we have inorganic structures. You see inorganic structures, there's a more broad distribution of crystal systems for those structures. But for organic structures, it's more skewed to the lower symmetry crystal systems. So triclinic, monoclinic, orthorhombic, I mean, the majority of organic structures are going to crystallize in monoclinic. And even there, we can narrow it down even further to about 5 space groups that about 85% of crystals crystallize in. So it even gets narrow. So it's a very select few of heavily used space groups. So here we just want to revisit unit cells. So we talked about at the very beginning, unit cells are the smallest repeat unit that contains all the symmetry of the crystal. So it just gets repeated in 3 dimensions. The unit cell has all the chemical, physical, and crystallographic properties of the crystal. It's a parallel pipette, and every unit cell is the same. The only difference is it's just been translated in the X, Y, or Z position. So now we're going to introduce some new guidelines, and one of them is that crystallographers like symmetry. So we like to choose the unit cells that exhibit the highest possible symmetry we can have. So we always like to go higher to get the highest possible symmetry. Now, sometimes when you choose a slightly larger unit cell, you can get higher symmetry in it. So for example, you can choose a larger unit cell, maybe the angles become 90 degrees or the edges become equal length. And so if you remember, cubic was the highest symmetry unit cell, so maybe there's something we can do, either move the angles closer to 90 or make all the lengths equal to get higher symmetry systems. And so now we're going to introduce a new symmetry element that can increase the symmetry of a unit cell, which is called centering. And this is called, excuse me, this is called, centering is a translational symmetry. So all we're doing is we're shifting lattice points. So how can we translate or center? We can center along face diagonals, and we're going to talk about all of these in just a moment. We can center across body diagonals, and we can center across multiple face diagonals. We're going to show you examples of all of these. And so the centering is determined by the position of the lattice points in the unit cell. So primitive, which is P, only has one lattice point in the unit cell, and typically the lattice point starts at the origin of the unit cell. Now when you do centering, you'll have more than one lattice point. So usually when you go from a primitive unit cell to a centered unit cell, the unit cell size increases for the sheer fact that now you have more lattice points in the unit cell. And so a typical number of lattice points for centered unit cells could be 2, could be 4. That's generally the most lattice points you can have is 2 to 4, depending on the type of centering. And centering is the second major level of classification for crystal systems, because we're going to see in a moment certain crystal systems can have certain types of centering. So here, just to give you an idea of the different types of centering, so we have primitive. Primitive symbol is P. So whenever you see a unit cell that starts with P, it's going to be primitive unit cell. Now what does a primitive unit cell looks like? It looks like this. So every lattice point is on a corner of the unit cell, and based on this, there's only one lattice point in a primitive unit cell, because remember, each corner connects to 7 other corners. So an atom on a corner is only 1/8 of an atom. So since we have 8 corners, 8 times 1/8 gives us 1. Next we have side centering. So side centering is centering along one of the sides of a unit cell. And there are 3 different types of side centering depending on which side. So we have A centering, B centering, and C centering. So what does that look like? it looks something like this. So again, you still have the lattice points for the primitive cell, but now you're introducing a second lattice point on the face-centered part of the unit cell. And so therefore, with side centering, you can have a total of 2 lattice points. Because remember, each corner connects to 7 other corners, so that's 1/8, and there's 8 corners, that's 1. And each face touches another face. So an atom on a face represents half of an atom. So since there's 2 halves, that adds to 1, so 1 plus 1 gives us 2. Body centering, this is denoted the symbol I. So you see I as the first letter in the space group, it means it's body centered. And now what we have is we have lattice points on the corners, but we also have a lattice point in the center of the unit cell. And this also has 2 lattice points. Lastly, we have face centering, which is denoted the symbol F. And it's kind of like side centering, but now we have all the sides have been centered. So not just one side, now we have the A side, the B side, and the C side all centered. So it's called face center. So every face has been centered. And since there's 6 sides on a face, and each face is half an atom, that means there's 3 atoms from the sides and 1 atom from the corners. So that means it has a total of 4 lattice points. And again, you got to remember, the more lattice points you have, the larger the unit cell is going to be. So the more lattice points contained within a unit cell. So this is showing you some examples. Here we have a body-centered cubic unit cell of cesium chloride. So you have 1 cesium ion in the center, and you have 4 chloride or 8 chloride atoms on the corners, but since there's 1/8, it's going to be a total of 1 chloride ion altogether. Then sodium chloride, here we have a simple cubic unit cell, and so you have ions on the corners of the unit cell. And so if you look, you have an equal number of sodium ions and chloride ions in one unit cell, which means because it's a 1-to-1 ratio. Next we have carbon. This would be carbon diamond, and this one, it's hard to see, but I believe it's face-centered, a face-centered type of unit cell, because you can see we have atoms on the corners and also atoms on every face. In addition, there may be one in the center too, I'm not sure. And then down here, this unit cell has a atom on each corner, an atom on each face, and an atom in the center. So this one technically would have, let's see, 5 lattice points. And if you look here, the formula is BaTiO3, and that adds up to 5. So that makes sense that you have maybe a barium in the center, titaniums on the corners, and then oxygens on the faces. Because there's 3 oxygens, and remember that there's 6 sides on a cube. Divide that by half, you get 3. So that's how we know that the oxygens are on the faces. The barium or the titanium would be in the center. Maybe it's the titanium. And then the other one is on the corners. Both of those add up to 1. So you get a variety of different types of centering in a unit cell. So now this centering brings us to one important aspect of crystallography, which was derived by Auguste Bravais in 1848. He was a physicist, and he developed something called Bravais lattices. It's an infinite set of points related by a set of discrete translation operations. So these infinite set of points are related through translation. And a couple of years earlier than when Bravais discovered this or developed this, another scientist, Frankenheim, proposed that there were 15 lattices that different crystal systems could have. And also he stated that it could be a duplication of rhombohedral and hexagonal and trigonal systems. So this is kind of the beginning of the types of Bravais lattices we could have. So first was proposed 15, and then Bravais came and said, you know, if we have an infinite set of points, they can be related by discrete translation operations. So we're talking about translation operations, not symmetry. So now we're going to talk about the different types of Bravais lattices. So there are 14 Bravais lattices, and again, the way we get a Bravais lattice is that we combine a crystal system and centering. And this is very important, this chart here. So what you'll see is for triclinic, the only centering we can have is primitive. So every triclinic space group is going to be primitive. So it's going to start with a P. Now with cubic, we can have primitive, we can have body centered, and we can have face centered. And this is important here. So pay attention here. Every cubic space group is either going to start with a P, an I, or an F. So again, every cubic space group will start with a P, an I, or an F in their space group symbol, because that's the type of centering. Now tetragonal can undergo two types of centering. It can be primitive or body centered. So now tetragonal, when we look at its space group symbol, it will either have a P or an I as the first symbol in the space group notation. Now orthorhombic is probably the one with the most types of centering. Orthorhombic can be primitive, it can be body centered, it can be face centered, and it can be side centered. Now, just because it's C centered, it can also be, don't be alarmed if you see, in addition to C centered, you may see A centered or B centered for orthorhombic. So there are some orthorhombic space groups that have A centering and B centering in addition to C centering. Now, you may say, well, why do they have A and B centering? You can always translate from A centering to C centering. So C is like the universal one when we talk about side centering, but you can also have A and B are, what's the word I'm looking for? Non-conventional types of centering and orthorhombic. So again, orthorhombic, you can have primitive, you can have body, you can have face, and you can have side centering, and the side centering can be C, A, or B. Now notice for rhombohedral, trigonal, and hexagonal, there can only be primitive centering. So whenever you see a trigonal or hexagonal space group, it's going to have P as the first element in the space group symbol. And then lastly, monoclinic. Monoclinic can be primitive and it can be C-centered. Now monoclinic can only be C-centered. Monoclinic cannot be A-centered or B-centered. Only C-centered for monoclinic. Now to give you a kind of a comparison with monoclinic, if you have a primitive cell and then you go to a C-centered cell, it actually doubles the volume of the C-centered cell compared to the primitive cell. And that's because you're doubling the number of lattice points in the unit cell. So when you go from monoclinic primitive to monoclinic C-centered, you're going to be doubling typically the unit cell, making it bigger. So you may ask, well, why is there only 14 Bravais lattices? Why can't triclinic be I, F, or C centered or trigonal be I, F, or C. So why isn't there a centering for every type of crystal system? And we're going to talk about that in just a moment. So why don't we have 28 or 35 Bravais lattices? So as we said earlier, these are the types of centering that the different crystal systems can have. And one reason why we can't have certain types of centering is because it's forbidden by the symmetry requirements of the crystal. So for example, for cubic cannot be C-centered because then it wouldn't adhere to the symmetry requirements of a cubic unit cell. Likewise, trigonal and hexagonal can't be C-centered, body-centered, or face-centered because again, it's forbidden by the symmetry requirements in that crystal system. So some crystal systems, symmetry or centering is forbidden due to the symmetry requirements of those systems. So for example, a six-fold, a three-fold, four-fold, etc. Now the other condition is that sometimes it's not necessary because there's no need to increase symmetry. And what do we mean by this? What we mean is that, for example, in triclinic, we don't need to describe it as C-centered, I-centered, or F-centered because by doing that, we don't achieve any more additional symmetry with it that can describe the centering of the cell more easily. So for triclinic, we just stick with primitive. And then third, others can be transformed to smaller cells of other centering. So if you remember, typically when we deal with crystal systems, we like to get the unit cell that has the largest or highest symmetry. So sometimes when we center along a particular, we do some centering, that will actually cause the unit cells to be smaller. And, or no, what happens is we can transform it into a smaller unit cell, therefore not needing the centered unit cell. So these are some reasons why we don't have 35 Bravais lattices, we only have 14. One main reason is the symmetry requirements of the crystal system. Another one is it's just not needed. It doesn't do anything to enhance the symmetry in the unit cell. So for example, if we have a three-fold or six-fold symmetry, centering actually breaks that symmetry. So for example, here, if we have a hexagon, six-fold symmetry, and then we want to center it, say we want to do body centering, which is what's shown here on the right, it's going to break up that six-fold symmetry. So that's why there's no body centering in three-fold or six-fold rotations. Now, why isn't tetragonal F or C centered? Because if we do a C-centered tetragonal system, we still have the four-fold symmetry, but now we have a smaller primitive cell. So this is why C-centered. Let me go back. I didn't think. Oh yeah, tetragonal can be C-centered. So with C-centered tetragonal, again we C-centered it. We still retain the symmetry, but we get a smaller primitive cell. And therefore we can get, since we have a smaller primitive unit cell, we should use that one, and that's why it's not C-centered versus primitive centered. Now, why don't we do a face-centered tetragonal? Is because when we do a body-centered tetragonal, it has half the volume, and it's the preferred unit cell. Now for monoclinic systems, why don't we have an I-centered or an F-centered monoclinic system? And that's because these are transformed to C-centered, and the reason we transform it to C-centered is because we want to keep the B-axis the same. And if we were to do body-centered, it would make a new C-axis. And so typically with monoclinic, we take I-centered and F-centered, and we transform it to C-centered, because that's the preferred center for monoclinic systems. So you will see sometimes space groups that report A and B centering, and the centering just means what face the lattice point will center on. So you can have A centering, which is the BC face, B centering, the AC face, or C centering, which is the AB face. Now, general convention is that side centering is usually set to the C centering by the selection of the axes. Now, for monoclinic, C centering is the convention, but older literature, you may see B centering reported. Now, C centering is important for monoclinic because, as you can see there, it relates the lattice points to one another by twofold symmetry along B, which is the unique axis for monoclinic. Now, orthorhombic, even though there's A and B centering in orthorhombic, it can be rearranged so that it transforms into C centering. So any type of side centering can be translated into another side centered. So you can go from A centered to C centered, etc. Now, in other cases, as we talked about, A and B centering would break rotational symmetry. So for example, for tetragonal, if you had A centering, it would break the rotational symmetry because in tetragonal, the unique axis is the C-axis. The same for hexagonal. You would break, if you had, for example, A centering, you would break the threefold rotational symmetry. And the same thing for cubic, it would break the fourfold symmetry along all axes. So that's why we don't have A or B centering for those types of crystal systems, because it disrupts the rotational symmetry. Now, how do we center a set of coordinates? Well, that's what's shown here, and this is important. So if we're A centering, it means you add a half to the B and C coordinates. So whatever side centering you have, you're going to add 0.5 to the other sets of coordinates. So if it's A centering, you're going to add 0.5 to Y and Z. If it's B centering, you're going to add 0.5 to X and Z. So the side that you're centering, you're going to add a half to the other sets of coordinates. And then C centering, of course, you're going to add it to X and Y. And that's how you generate the side centering coordinates. So for example, if we want to do C centering for the coordinate 0.2, 0.3, 0.7, since it's C centering, you would get 0.7, 0.8, 0.7. So you would actually have two sets of origins in this unit cell. One is the primitive, one is the C center. That's where you get your two lattice points from. And this is going to be probably blow your mind, but when you have a C-centered space group, you're going to have double the number of symmetry elements, because you're going to have symmetry elements for the primitive lattice points, and then you're also going to have symmetry elements for the C-centered lattice points. So whenever you incorporate centering, you're going to have symmetry elements for both or all the different lattice points. So for C centering, if you only had two symmetry elements for primitive, you're going to have 4 symmetry elements for C centering because two of them are on the primitive lattice point, two of them are on the C centered lattice point. Now with body centering, we just add a half to every coordinate. And again, body centering would have two sets of symmetry elements for each lattice point. So one lattice point is at the origin, the other lattice point is at a half. For face centering, here we're just doing side centering, but we're doing it for all the sides. So you add a half to X and Y, you add a half to Y and Z, and then you add a half to X and Z. And so for face centering, you can see here that you have 4 lattice points. So this is 1, 2, 3, 4. Now, if we say the primitive has 2 symmetry elements, when we go to face centered, it's going to have 8 symmetry elements. And the reason it has 8 is that you have to perform the same set of symmetry elements on every unique lattice point. So there's 2 on this one, 2 on that one, 2 on that one, 2 on that one. So a F-centered unit cell is going to have a lot of symmetry elements in it. A body centering would have, if the primitive had 2 symmetry elements, then body would have 4. Because you have to perform symmetry elements on both lattice points. And so typically centering in most cases leads to a bigger unit cell because again you're introducing more lattice points to it. So here we have an example. We have this compound yttrium 3 iron 5 O12. In the body centered cubic it's 1895 angstroms cubed. In the primitive reduced cell it's 947. And so you'll notice that the volume is exactly double for the body centered cubic cell, and that's because body centered has 2 lattice points, primitive has 1 lattice point. So since you doubled the number of lattice points, you're going to double the unit cell. Now, it's convention to use usually the reduced cell, and whenever you run crystal diffraction experiments, typically what you see is the reduced cell listed. And the reduced cell is important because when you're doing a search on the data on a crystallographic database for unit cells, typically you want to use the reduced unit cell so that it takes that reduced unit cell and translates it into bigger unit cells so that you can get a more broad search of the database. So reduced unit cell, what we're doing is we're looking for the 3 shortest non-coplanar directions, so the 3 shortest axes, the smallest possible volume, so typically it's primitive, and the axes are listed in ascending order. So you start from the shortest to the longest. If it's a centered cell, typically these are reduced to primitive cells. Now, if it's already in a primitive unit cell, that is the reduced cell. You can't, there's no transformation to reduce it further. So only centered cells get reduced to primitive cells. And that again causes the volume to decrease because you have fewer lattice points and the axes decrease as well. So typically when you do a search, you do it using a reduced unit cell. So it removes the centering from the unit cell. So just to show you an example of some reduced cell transformations of tetragonal. So tetragonal have body-centered cells. And our first option could be that we have a reduced cell where A equals B equals C, alpha beta not equal 90, gamma is not equal to alpha and beta, and it's equal to not equal to 90. So if we centered this, body centered, we get a tetragonal unit cell. So A equals B not equals C, alpha beta gamma equal to 90. So before we centered it, when it was primitive, we couldn't deduce what crystal system it was. But when we body centered it, we determined that it was tetragonal. Now you see the reduced unit cell, A equals B equals C, is 5.935. And of course, we have the cell angles. But when we center it, now we notice that the cell axes increased. Because again, what we're doing is when we center it, we increase the size of the unit cell. Here we have another compound, it's uranium trioxide. So again, the reduced cell, we have all different angles. A equals B not equal to C. But when we center it, body centered, we set two axes equal to each other, and we set the angles equal to 90. You see the difference in the reduced cell and the centered cell. So again, what you're seeing here is that the centered cell is larger than the reduced cell. Because again, you're incorporating more lattice points. And then we'll just look at one more orthorhombic. When we have a side-centered C orthorhombic cell, and so when we have a reduced form, we see that none of the axes equal each other. Alpha, beta, or gamma are not equal to 90. But when we do a side centering, we see that now we get alpha, beta, gamma equal to 90. And therefore, we have an enlarged cell. So you see that the center cell, the B axis, is a lot larger than the B axis of the reduced cell. And what you got to note here is that when we do a centered cell, the B axis and the C axis switched because we did C centering. And notice that the B axis on the centered cell is twice, roughly, of the C axis on the reduced cell. And the way they get that is by using this equation here. Okay. So that concludes crystal systems. And the main things you should grasp from this lecture today is what types of centering are allowed in different crystal systems, what type of rotational symmetries are allowed in crystal systems, how many lattice points do we have for the different types of centering. Also know that the 7 types of crystal systems, and understand that when you do a centering from primitive, you're usually going to increase the volume of the unit cell. And know that there are 14 Bravais lattices, which can combine crystal symmetry, crystal system with centering. And so from this, in the next lecture, we're going to look at, now we're going to be assigning space groups to these crystal systems, which have a unique set of symmetry elements. And it's very important that you know the point symmetry groups, because that's going to be very helpful in assigning space groups to crystal systems. So I'll go ahead, we'll stop the video for today, and if you have any questions, feel free to ask.